I'd like to welcome you to the Computer Science Distinguished Lecture Series. Our speaker today is Erik Andersen. As you can see from the slides, Erik is our own graduate who finished in 2007 with a Bachelor in Computer Science, getting the degree in highest honors. Erik actually is from Chapel Hill. For those of you from Chapel Hill, he went to Culbreath Middle School and East Chapel High School. So it's great to have him back again. And for those of you who were in that department from 03 to 07, may have interacted with Erik, you taught him, advised him, or even some of the staff members remember him. I should just tell a little bit of personal story, how I met Erik. This is 2005 spring. Thanks to somebody, maybe it was Kevin, the director undergraduate, they made me Erik's advisor. And whosoever that was, thank you. In those days, we used to get an orange folder, and he was supposed to be the advisor to get a PIN number, like he was forced to see me. He comes to my office. Here I see a small frame kid, if I may say that, for your permission. And I said, oh, what are you doing? I'm a sophomore. So I started advising him, oh, you're a sophomore. You must have taken this old course number like 114, which is 401. He said, I've done that. I said, you take data structures? I've done that. You should take the algorithms? I've done that. So literally here I'm sitting in my chair, a guy with a small frame who looks like barely like a high schooler, is a sophomore in our program, has already taken the most challenging course in our curriculum, and is virtually not being challenged. I say, what can I advise you? You can advise me. Anyway, since I saw this amazing guy, I kind of brainwashed and steered him to our research. He took graduate courses, worked with Ming and I in the junior and senior years with us, on a team working crowd simulation with the team, and published, I think, 5 papers in very top places. 7? Okay, can't keep up. After that, he went to University of Washington, did a PhD in graphics and gaming. He'll tell you all about it. And just about a year and a half ago, he entered the faculty market. As some of you know, there are always these 6 or 8 candidates who are on computer science faculty's most wanted list. Every department wants them. So Erik was one of those hot candidates in spring of 2014, got multiple offers, and now is a professor at Cornell, which, as you may know, is one of the top-rated departments. If you look at his resume, he has done amazing work in graphics and more recently in game and HCI, getting a lot of best paper awards. And not only that, he has developed educational games, which got award from Disney and NHK. So let's just welcome Erik back and listen to his new work on what he thinks is the next grand challenge in designing engaging learning experiences. Welcome, Erik.
Thank you. Thank you. I'm really excited to be here. It's a huge honor. And my talk is about engaging learning experiences, but I also wanted to talk about an important event in UNCCS history that I assume nobody knows about. And this is related. So in 2005, there was this DARPA Grand Challenge, which was one of the things that really got the ball rolling on self-driving cars. So there's all these cars driving through the desert, trying to get to the goal. It was very exciting. There was a whole lot of publicity. And Dinesh at the time was teaching a robot motion planning class that I was involved with. And he wanted to have something with a similar excitement. We didn't have cars or deserts, but we had these Sony Aibo robots that I had been working with. And so we had the Sitterson Grand Challenge. There was no Brooks building at that point. It's all Sitterson. And basically, there was this traffic cone, and we scavenged things from the graphics lab to make an obstacle course. And basically, it was this grand challenge of each team of students had to program this robot to navigate through this environment to get to the orange cone. And I wanted to talk about this event for a couple reasons. One, this was my personal entry into research. So I spent a whole summer messing with the Aibo and figuring out what it could do. But secondly, it taught me the importance of engagement in education, that packaging really matters. And so I want to tell you about the class that I've been teaching. So I teach a video game design class at Cornell. And I thought, OK, what kind of grand challenge should I give them? And the grand challenge I came up with is I want you guys to design video games that are going to get played by as many people as possible. So we designed the class in a way that they would produce games in teams of 6 students, 4 programmers, 2 artists, and then they have to release their games on these web portals. So this is Congregate. It's a website that 10 million people spend 23 million hours a month playing free online games. It's a huge sink of human attention. And basically, this is their exam, right? They make a game and they release it to Congregate. And this screenshot was taken when we basically owned the front page. So all of these games in the hot new games list on this day were from the class. And totally, we got 190,000 people to play the games, which was super exciting. Like, the students were really, really into it. And the games got reviews from like external websites, and so the students got named as contributors to this. And it seemed like it was really fun. And so I like some of the design of this course was inspired by the Sitterson Grand Challenge and also by Diane Pozevsky's software engineering class that I took when I was here. And it also made me reflect a little bit on what are the grand challenges in education as a whole, right? So people have been building educational technology for a while, but there's been this huge surge of excitement, especially in the last 5-10 years with MOOCs and Khan Academy. And I think we may be at sort of a similar moment where it's worth thinking about what the grand challenges are. And for me, especially as I'm starting to educate people more seriously, it's clear to me that although education is something that we all care about, it's really, really, really hard, right? And despite all the best efforts that we put into this, in many cases we still don't do very well. And a huge source of this comes from the complexity of individual students, that for any group of students, some of them are going to know what you're talking about and some of them aren't. There's a huge variance in skill level and interest for any topic. Students can get confused in every way you can possibly imagine, and they're constantly coming up with new ways to get confused. And as the student gets better, we need to be able to continually provide material that will help them grow. And traditional methods of instruction are not great for this, right? So case in point, the lecture format, right? What I'm doing right now. Statistically speaking, I have about 20 minutes before most of you have zoned out, right? And there's even the best students, even the most motivated students have a hard time focusing. And they might come back and start paying attention again, but then they'll zone out again. And this is just a fact of human nature. So only 30 or 40% of what is taught in a lecture gets retained, which is why everyone crams for the exam every time. And so I think part of what makes things so hard to design has to do with the way that we do it. So the current workflow generally is that there's some educator who thinks, I want to teach something like algebra. And through some process of design and iterating, they come up with some content. And then they deploy that content into a classroom and they get some feedback. And then they sort of iteratively improve this as they go. And one of the problems is that the instructor has to make a huge amount of assumptions as they do this. Like thinking about what order should I present concepts in? How much should I reinforce each concept before moving on to the next one? Should I spend time working on lecture or should I make better practice problems? What practice problems should I give? Where should these come from? So these are all questions, and generally, although we have educational theory to draw from, usually instructors are doing this in kind of an ad hoc manner, which is why all the programs are different, everybody disagrees forever. And in contrast, I argue that we should not make assumptions. And my work has looked at this in two respects. So one of them is, can we create content automatically by modeling the student's thought process and lower the barriers towards creation of educational content? And then I've also looked at how can we refine content through large-scale experimentation, so there's less guessing, more trying. And this leads rise to a way of doing educational development that I'm calling active discovery of learning content, in which the educator encodes target knowledge that they want to teach, and then the goal is to get this to millions of people. So we consider what are the engagement parameters of these people? What do we need to do to keep them excited, engaged, and interested? Then I've explored using automatic generation techniques to create things that teach this knowledge in the most engaging way, which produces content, and then we need a way to get it to these millions of people, which I've been using educational games as a way to do. And then we record what they're doing through analytics, we store it in a database, and we refine the generators and produce theories that help improve education as a whole. So this whole complicated flowchart is going to be the outline of what I'm going to talk about, and I'm going to talk about different pieces of it. So first I'll talk about the games that I made and how we've been able to get millions of people to play them. Secondly, I'll talk about some of the more computer science programming languages part of this, so how we can borrow tools from software engineering to help us create educational content automatically. And then also the refinement, how we can then make this iterative process that through deployment to large numbers of people, we can improve the content. So first, let's start with the games. So in 2008, the US National Mathematics Advisory Panel, which is a government body that advises on educational matters, found that difficulty with fractions is pervasive and a major obstacle to further progress in mathematics. And this is one of 4 topics that they identified as being particularly problematic. Another one was algebra, another one was word problems. And so we thought we could target this as some way of making a game that would be both educational and fun. And we wanted to make something that was not just taking an existing game that was great and ruining it by adding math to it, which is the way a lot of edutainment is developed, but instead make something that we really wanted to play ourselves. So I worked on 3 games. One is called Refraction, another one's called Tree Frog Treasure, another one's called Creature Capture. I worked the most on Refraction, so I'll talk about this. Basically, the idea, it's a free online Flash game. When we developed it, Flash was still a thing, but it still works. And basically, the idea is every level there's a laser, and then some spaceships that want a fraction of the laser. In this level, they both want 1/2. And the player is given these pieces over here that they can move, and they can put in the path of the laser to split it. And so the goal is to get the right amount of the laser to all the targets at the same time. So here's me trying to solve it. I now have split this one, so this spaceship's happy, and now that spaceship's happy because they both got 1/2. We call this euphoria, so we give them fireworks. The goal is to make the students as happy as possible. And we released it through a variety of websites, and it was a huge success. So roughly 1 million people have played it. This is Bill Gates talking about it. I made this slide for him. A lot of the work was funded by the Gates Foundation. We received awards from Disney and from NHK. NHK is like the PBS of Japan. And for that, I got to go, and I was on TV in Japan. So here they are talking about the game. But we also need to measure that it actually has educational value. And this work is ongoing, but a pilot study that we did used a company called K-12 that produces online curricula for homeschool students. We recruited 3,271 students through K-12, and we tested the effectiveness of refraction by giving a pre-test and then having them play the game and then giving a post-test. This is kind of a standard way that educational software is evaluated. And not everyone made it to the post-test, so only 1,103 did it. It was not a compulsory activity, so there is some survivorship bias here. And the pre-test, post-test had a bunch of fractions-related questions that were related to the topics that are taught in the game, like basically equal partitioning. And there was a 5% improvement from the pre-test to the post-test. And you might think 5% isn't huge. The educators we talked to say that at this scale, actually, improving things by 5% is a huge deal. So we've been excited by this. And some of the other games have also shown consistent, statistically significant learning gains for fractions as well. Tree Frog Treasure of about 10%. More recently, I've been working on games for language. So I made this Thai alphabet game that I'll talk more in detail about, and also a game called Crystallize. So when I was a UNC student, I took lots of language classes. I highly recommend it for those of you for undergrads. It was really fun. And I started taking Japanese when I was here, and I was kind of simultaneously excited and mystified by it. And it's been something I've studied for a while. And I'm convinced that the way that we do it, while certainly a lot of people have put a lot of effort into it, could be greatly improved, perhaps by technology. So I tried things like Rosetta Stone, which is basically a $500 tool that you click on various pictures, and it's asking you to translate various phrases by clicking on the picture. I've also tried Duolingo. How many of you have tried this? It's pretty cool. like you also are learning by translating lots of sentences. And I got pretty far, but then I got bored. And I was thinking back to some of my experiences and realizing there's a whole lot of this that's getting missed. Like, there's some things that are lost by this whole approach. So I studied abroad in Japan when I was at UNC. These are some of the pictures that I took. There's a whole vibrancy that's lost, right? Like, people study language for a reason, so that they, I mean, many different reasons, but some of them so that they can actually go somewhere and use it. And all of this fun, all of this cultural information is getting lost. This picture actually won a competition at the student union when I was here. In particular, people learn more through things like context, right? So if two people read each other and one of them says hello, hey to each other, right? What do you think that means? Given the context, hello, right? Especially if they're waving. Another example is learning through inference. So say there's 3 things on a table, and somebody says, get me the upk, and I don't know what that is, but I know this word aplerstay and onfe, right? But I don't know this one. So which one do you think this is? This one, probably, right? I mean, you don't know. Maybe there's another word for aplerstay that's rare or something. But with this in mind, I've been working with some students at Cornell to make this game called Crystallize, which is this 3D immersive game that you can download. It's crystallizeonline.com. And basically, you walk around and you talk to friendly people, and you say things to them. And some of the thing that we really wanted to try to innovate was you can pull the words from the context. So here I am, like, pulling words, and they become inventory items as I go about my adventure. And then there's all these quests that are there that you can complete. There's jobs, so you can become like a cleaner, and then you're getting instructions about like what to clean. And if you clean the wrong thing, you get fired. And so that, and we managed to gamify some of these things we wanted to. So this task is asking the player to find the word goodbye and say it to that person, right? And nearby, there's somebody saying the word while there's a context-relevant action. So the player can kind of infer that this might mean goodbye. Similarly, there's a lot of scaffolding. So this is explaining how to say I'm a student. And at first, it gives you some of the words. And then slowly it takes away that scaffolding so that you can learn to create more and more complex sentences. So this is all very new. We released it over the summer, and we got through Reddit, actually, which is a really fun way to do a release, by the way. Like, we did it through a subreddit for Japanese focus, and it got upvoted to 100 pretty quickly. And we got 186 people to play it, and like over 80 of them left comments. So we actually could do like a usability evaluation of the tool by looking at which comments got upvoted the most. And we found that some of the players got really engaged. So 20% of the players played for an hour or more, and they collected more than 60 words. On average, people learned an average of 9 words in an average playtime of 41 minutes. So we need to compare it to existing methods. My hypothesis is that it might be a little slower than using Duolingo, but I think that hopefully we can engage people for a really, really long time by creating this sort of sense of incentives that help people learn. So this is ongoing. This gives you an idea of some of the games that I've worked on and how we can deploy them to millions of people. Now I'll talk a little bit about some of the more computer science parts of it, of how can we create content for education automatically. And part of the reason we want to do this is that this is a huge bottleneck, right? So there's these things called intelligent tutoring systems, for example. This great work out of CMU. They're these systems that the student can solve problems in, and it gives them personalized feedback. Some of the first computer technology that can really do a lot of personalized instruction. But it takes 300 hours of effort to create 1 hour of content, right? And the reason is because when you have adaptive education, like it's not that every student is doing the same thing. Every student is doing different things, right? So the authoring effort that's required to create that first thing, which was already hard, is now compounded by the need to complete multiple things. So the way that we currently do this is we think about, okay, this is the knowledge I want to teach, and then we create practice problems, explanations, feedback, even whole video games to teach this. And what I envision instead is going the other way. So we're going to encode the knowledge we want to teach, and then use this to generate everything. borrowing techniques from software engineering and programming languages. To make this work, we need a model to work with, and I've looked at procedural learning. So this is things like addition, where there's a step-by-step procedure that the student is learning, and that's the learning goal. This is also used in following a cooking recipe, something like fixing an airplane, solving refraction levels. I'll explain how pronouncing words in Thai can be looked at as a procedural problem. It's not everything. It doesn't cover factual learning. It doesn't cover conceptual learning. These are things that we need to address later. But a lot of learning can be expressed in this way. And so I worked on a number of things, basically generation systems that can take as input a program, that is the knowledge that we want to teach, and then produce things like practice problems, demonstrations, and also some neat work on trying to diagnose misconceptions automatically. So I'll talk a little bit about some of these. So for practice problems, like the standard way that we teach you how to do addition is we give you practice problems that we want you to solve. And it's very important how this difficulty gets higher, right? Like, you know it when the difficulty's right. Here's a student playing in one of the games, right? Like, they're happy. They have the challenge that's matched to the learner's ability. And if it's too fast or too slow, we don't get this. So we need basically problems that get more difficult over time. And ideally, we want a lot of problems so that we can carve whatever path through this space that we need for helping any particular student. So this work has looked at how can we create a whole set of problems automatically just from a description of the procedure so that we can take whatever path that we want through it. So to talk about this a little bit, I'll show an example. So this is a worksheet from a Canadian math textbook called Jump Math that's used in about 15% of schools in Canada. It's teaching students how to compare two numbers and figure out which is larger. So this should be something that most of you did in second grade. And this is the process that they're trying to get the students to learn. So the teacher's manual will talk about this, right? But this doesn't get taught explicitly to the student. Basically, they're being asked, if one number has more digits than the other, then you can figure out which number is bigger. This is assuming no decimals. Otherwise, you have to actually look digit by digit. So we made some observations that with this, we can identify important problem types and then also generate practice problems, compare progressions, and generate progressions. So how can we identify important problem types? It's similar to notions of code coverage in software engineering for test case suites, right? Like, we need to make sure that we have test cases that are going to cover all of the interesting pathways through this particular function. How do we generate practice problems? There are tools that do this automatically for software testing. So there's a tool called PEX that I really like. It's produced by Microsoft Research. It works for C# programs. There's other ones like this, like F-shell for C. And basically, you give them a program, and it'll try to create test cases that will cover the whole program. So it iteratively will generate new test cases and then figure out what parts of the program it's able to cover and then keep generating more. So we use this to generate like math problems. We tried this for addition, for subtraction. This is better than just enumerating lots and lots of problems because we can be sure that we cover the important space quickly. Now I'll talk about comparing. So often books are different in what practice problems they have. So the Jump Math one, here's a visualization of the problems in this particular worksheet. Basically, it starts here, and then it moves here. It follows the arrow. So each arrow is a change in problem type. And I've used, the letters are basically when, I forgot to show this. So like at various points along the process, it will output a letter. So these are basically showing different problem types. And then we can compare this to a different book. So this is the Singapore math book for the same exact topic. And the progressions are totally different from each other. It involves different problem types. There's some problem types in the Singapore one that don't show up in the Jump Math one at all, meaning that the teacher's manual basically told the teacher to tell the students about something that the problem set never exercised at all. And so what do we conclude? That the choice doesn't matter, that either of these progressions are optimal? What's more likely is that neither of them is the best, right? And once we have a language that we can use to describe how a particular problem set is increasing in difficulty, then we can have a way of proving this iteratively through data. So to generate the progressions themselves, now we can actually look at the what happens when you use the program to solve a particular problem. So I think most of you would say that the one on the left is easier, right? Because it basically is contained within the problem of the right as a subprocess. So using this metric of guessing that problems may be harder when they involve each other as subproblems. I haven't shown you the algorithm for this, right? But these are basically parts of that. Are letters outputted as the procedure is executed. We can see that the procedural steps of the top one are contained with the one in the bottom. Similarly, I think most of you would agree that this problem on the right is harder because it involves all the procedural steps on the left. In addition, you have to deal with this carry, right? And this also is something that shows up when we look at what steps are required to solve the problem. So we can create a partial ordering of practice problems for anything that we have a procedure to solve. And we applied this for a number of different ways to build both the partial ordering graph of problems and then also to walk along it using something like a topological sort. So we applied this to refraction first. There was an expert level progression that we had an expert game designer who spent 100 hours roughly making. And he did this all by hand. And we created an automatic one using this technique. So we wrote a program that solves refraction levels. In that, it does some fraction math. It also does some spatial reasoning. And then we didn't use PEX for this. We used answer set programming, which is a constraint-solving AI technique. But the same basic idea, right? We created basically test cases for this process that we want the students to learn to solve these levels. And then, once we had those levels and we could order them in terms of difficulty, we constructed an automatic progression that followed the same rate of increase of difficulty as the original one. And then we did an A/B test with 2,377 players. We released this as Refraction 2, but actually half of the people got the original game. And nobody complained. I was sort of surprised. And the engagement was roughly the same. So we were able to get people to play for about 95% as long with this automatic one, which to me was a big deal because it took 100 hours to create this original expert progression, and we were able to create this automatic one by just pushing a button. I mean, we had to write this procedure, but there wasn't any other input to the system. I also applied this to the Thai alphabet, which I didn't know, and I wanted to use this as a way to learn it. So basically, I wanted to learn to pronounce kind of like I would have when I was 1 year old. I wanted to learn one letter and then start pronouncing syllables and then full words and then more complicated words. And so I made a progression for the Thai alphabet in the same way. I found a program that transliterates words in Thai to English. And then I found a dictionary of words of the 1,000 most common words in Thai. And using these two as input to the system, it creates this game, which is not very smart, where basically I'm just transliterating longer and longer strings, and it's moving through this large partial ordering of words, right? So it knows which ones contain each other in terms of sort of procedural subproblems. And I released this online and got something like 3,000 people to play it, and most of them ran away immediately. But there's something around 80 or 100 people that actually transliterated all 800 words. And that means they can basically transliterate any word because of the way that these words were chosen. And I have a hypothesis that not all of those 100 people intended to do this, right? That if you play it, you'll notice it ramps up. It's built so that you can keep getting further without knowing anything. So these are some applications of how we can create practice problems. I'll talk a little bit also about how we can diagnose misconceptions. So first I'm going to give you guys a little exercise. So this is a student who is trying to solve an addition problem, and she's very confused. Can anybody tell me what she's doing? Subtraction? Okay, so this 5 is this 8 minus this 3. That's true.
And she's subtracting the 3 from 4 as well.
Okay, so subtracting 3 from 8, 5. Subtracting 3 from 4, 1. Does that work over here? Not really. So no, not quite. So it solves one of them. Yes?
Adding all the individual digits?
In what circumstances?
So on the top, a 4 plus 8 is 12 plus 3 is 15.
Okay. What about here?
17 and 20.
So this is real addition. This actually works, right? So you're almost exactly right, right? So like when there are 3 numbers, the student is adding all of the digits she sees and writing the sum below it. Otherwise, she's doing the right thing when there's 2 full columns. And when I started studying the errors that students make, there's tons of these. There's more than 150 that are known just for subtraction that are this kind of thing. They're systematic errors that happen because the student is incorrectly using things that they learned before. Yes?
Did anybody ever represent the first problem as 4, 8 plus 0, 3? To see if that problem actually went away.
I don't know. I was looking at it secondhand from a book that was looking at these errors, and like I didn't have the opportunity to experiment with the students. So I picked this example, one, because students are always coming up with new ways to be confused, right? So like we can't prime a system ahead of a time to know all the things that the student might do. The student does a lot of these, and it's hard, right? So what Dinesh said was true for this one, but it didn't match all the other ones, right? So it's a complicated process. Teachers are doing this all the time. They spend a lot of time grading. I spend a lot of time grading, not exactly this. And this is something that would be great if we could do automatically. So more formally, what I want to do is I want to go from a set of solved demonstrations to some representation of what the student is doing, right? In this case, I'm actually going to learn their program. And I'm not going to learn just one program. I'm going to learn all of the programs that describe all of the examples that I have seen. And once I have this, then I could do something like take them exactly to the problems that I think they're going to get wrong by looking at which ones does their procedure solve wrong and the correct procedure solve correctly. So this is actually similar to an existing body of work called programming by demonstration, where the goal is to create programs from demonstrating their behavior. So how many of you have used Excel 2013? I hope everybody. How many people have used Flash Fill? Has anyone seen this? So you have. It's the coolest thing that you don't know is in Excel. So basically, like, say I have a set of phone numbers and I want to change the format. I give one example of what I want, and then I drag this down, and then I click Flash Fill, and it will fill it in. I swear this is there. It's the coolest thing. And it saves me so. Once I knew this was there, then I start using this all the time. And essentially what this is doing is it's trying to reconstruct your thought process, right? Like my thought process for this was I'm going to try to put parentheses around it, and I'm going to put a space, and I'm going to put a dash, right? And there's some analog here to what students are doing in math problems, right? Like this system can reconstruct what an end user is trying to do for spreadsheet automation, maybe we could use a similar idea to reconstruct a program that describes what the students are doing. So this is what we did. Basically, the idea is for every example, we're going to learn the base operations, like very simple ways of describing like the simpler concepts that the student has learned is now composing incorrectly. We'll learn control flow over this, and then we'll do this for each example, and then unify all these examples together. So this is doing it by exhaustion. You could imagine using other kinds of probabilistic or AI techniques, and we're doing this exhaustively. And some of the ideas that we're borrowing are data structures that can represent huge sets of possible programs efficiently. And then also, we invented a new synthesis algorithm that will describe to do this. So let me give an example. So we'll learn the base operations for this one on the bottom. So basically, we assume the student is writing into a two-dimensional spreadsheet, and they're writing digits one by one. And each time they write a digit, there's some reason why they wrote that digit, right? So why might they have wrote this 9? It could be this 6 plus this 3. What else could it be? 3 times 3. It could be, there's actually 2 different 3s. So it could be either of those 3s plus this 6. So we prime the system with operators like this. And then we go through and exhaustively search through these and store them as hypotheses for each number that we do. So similarly, the 5 could have been this 3 plus this 2. It could have been this 3 plus this 2. And then we get a library of these base operations that only do one thing. And now we need to learn control flow over these. So one example of this is loops. So basically, if we detect that we have similar operations that happened at different times, that we have some hypothesis that looks like it may have actually been one process, we can pull this into a loop. And that becomes a new hypothesis, that this was actually a repetitive operation. And it turned out that actually there was no system that existed that could scale to this kind of problem that could learn nested loops or conditionals inside loops. So we invented a dynamic programming approach that would work for this. So the idea is we learn loops in phases. So first we might hypothesize that these 2 are part of one process that executed twice. And then we can apply this process more than once. So say in this case, I think that I can learn a loop to represent these, right? And now I have something that I can pull into a nested loop. So we do this dynamically in this way. So I've shown how we can learn the base operations and the control flow for this example. And the next step is to do this for all of the examples, and then we do the unification. So if you remember, there are two cases where there were full 2-column problems that the student seemed to be doing the correct thing. And then there are these other examples where the student just added all the digits. We need some conditional that can differentiate these, right? And so we also give it some Boolean operators that just check various facts about the spreadsheet as a way of figuring out what it could do. So in this case, that condition is, we had an operator of how many, is there a digit missing, I think was the name of the operator. And to do this, we use templates. So basically, we take advantage of the fact that the programs are usually pretty small. And we can just enumerate all of the conditional structures pretty easily. And so we just try them all. And we do this also in each loop learning phase. So to evaluate this, we looked at this book. This is Error Patterns in Computation. It's a book that's trying to train teachers how to find these kinds of errors. There's 40 errors in here across, I think, 10 different math topics. And they all look like this. There's a set of demonstrations that the teacher is given as an example of it. And we found that our system was able to diagnose 70% of these. So 29 out of the 40, which we thought was pretty exciting. When I say diagnose, I mean that the system was able to synthesize a program that reproduced all of the demonstrations. In most cases, it was a single thing that was left after the unification, right? So at the unification phase, we're throwing out programs that are not consistent from all the examples. So it has to match all of them. And in some cases, there was multiple hypotheses left at the end, and this is something that you would need more data to disambiguate. But it's exciting because I think that this is the kind of thing that can lead towards a general approach where we only do a little bit of work to give the system the knowledge of what these base concepts are, and then it can learn a whole bunch of programs that the students might be able to use. But it could not diagnose things like word problems. So there's some of the things in that book were word problems that don't fit into this structure at all. So this gives you a little bit of a flavor of what the generation part of this system is, right? How we can create content automatically by borrowing tools from software engineering. And I'll talk just really briefly about how we can refine this content once we deploy it. So how many of you have heard of gamification? Probably a lot of you, right? So this is something that's become a bit of a buzzword of like, how can we make people do things that they don't want to do by making it into a game? So for example, Khan Academy has these badges that you earn, and a lot of educational software has these, a lot of games have these. And we wanted to do an experiment to see what they were actually doing. So in 2 different games, we conducted an experiment where we looked at the effect of adding secondary objectives. So like coins that you can decide whether or not you want to get. We tested it in 2 games. This is a game called Hello Worlds. It was a game developed in a precursor to the class I taught by my advisor at University of Washington. This game has been played by 1.5 million times. And it was made by a team of undergrads. It has these coins that you could see that you pick up. And then Refraction also has these secondary objectives, these coins that they basically encourage the player to find a more complex solution to whatever it is they're trying. And we did an A/B test, so nothing super sophisticated. Basically, we got 27,000 people to play, and some of them got the version of the game without the coins, and some of them got the version of the game with the coins. There were flame wars that got started on these websites where people were arguing about, like, I don't understand, your level doesn't match mine. And nobody seemed to figure out that actually there were different versions of the game, that people weren't all playing the same thing. And we looked at metrics of engagement. Like, we looked at how far people got, how long they played, how likely they were to return. In the world of free online Flash games, we felt like these were pretty good metrics because they can just play another game if they want to. We used Congregate also for this, and they graciously put us on the front page while we were doing this. And we can visualize how engaged people are with charts like this. So the x-axis is time or progress or something, and the y-axis is the percentage of players who are there for at least that amount of time. And our assumption was that by adding secondary objectives, we're going to push this whole curve to the right, like encourage people to play longer. And that might have been naive. Maybe it was only going to be these expert players that are going to play longer. Like the people that are playing for long amounts of time might play longer to go get all these secondary objectives. This is what actually happened in both of the games. So there's 8,000 people in both conditions. And the red version is the one that has these secondary objectives for refraction. And we found that it did do better for this long tail. But there's a surprisingly large group of people that quit earlier. For Hello Worlds, we saw the same thing. The effect is a little smaller, but we also saw this drop off. And in refraction, this was so severe that basically they canceled each other out. So the total amount of time played by players in both conditions was the same, meaning that all of the extra time that people played in order to get all these things was canceled out by the people that quit because they got frustrated by it. And so we thought, this is odd, right? Because a lot of games have these kinds of things that work well. We figured maybe it's too hard. So we took these hard things and made them all really easy. Now they're carrots that were hanging in front of the player to try to get them to do the primary objectives. So this is another version that we tried, and we found that this did even better, right? So that we got people to play longer among the long-term players, but we didn't suffer this same drop-off. And we saw this effect in the other game as well. So there's a lot of things that we can learn from this. One of them is that incentive design is tricky. But this showed that we could use games as a way to answer questions in HCI and learning science. And there's an iterative design process that this leads to in which we can actually test the impact of key design decisions along the way, instead of just assuming what's going to happen. So this is a process that we've since used to improve the games. OK, so now I've motivated all the pieces of this, I hope. And this is ongoing work. The long-term goal is to be able to create optimal learning pathways for every student, for every topic. This is really hard. I'm probably not going to be able to do this. But I'll talk a little bit about what I mean. So for optimal learning pathways, I mean that I showed you this before, that we want practice problems that can get more difficult over time. Right? We can use something like reinforcement learning to figure out what the best pathways are. Right? So if we try various progressions and then see how they do, the hope is that we can eventually optimize and figure out this is the best way of arranging the content, right? And I also want to do this for each student. So trying to figure out if there's something about the student's behavior that makes a certain approach more likely. Can we cluster them? Can we figure out optimal ways of teaching each particular group? For every student, there's things that we could imagine, like how much should we reinforce each concept? How often should we combine concepts, right? So now that we have sort of an alphabet that we can use to look across various procedural topics, these are questions that we can start to answer. And I wonder if there's things that we can discover that will generalize across multiple domains. I'm also interested in applying this to other kinds of topics as well. So for example, we'll skip this. I've been interested in language. And so far, we've made this game that can get people to do basic alphabet and some basic words. But you can imagine applying the same framework to analyze syntax parsing, right? So we'll look at grammatical difficulty and rank sentences by how hard it is to parse them, and what problems, what parses are sub-parses of each other. So my hope is that we can produce like quests for Crystallize that are like gradually getting more difficult using the same basic technique. And now the inputs, the test cases that we're generating are sentences to verify whether or not you can understand the grammar of something. I'm also very interested in doing, trying to push the experience of Crystallize further. So the whole hope is that by simulating being in a place, right, that this may be a more engaging and effective experience than something like a textbook. So we've tried this in VR, and I'm really interested to see if we can put you in the situation of needing to order something in a foreign country, or explaining to the waiter that your friend is a vegetarian and can't eat certain things. Is this something that we can train people to do better using this kind of a system than through just reading things from a textbook? I'm also interested in trying to apply this to programming. I'm interested in what kinds of thought processes people are going through as they go from a problem specification and write programs. Is this something that we can proceduralize in the same way? This is also hard, but this is one of the problems that we're looking at, and then hopefully we can grade programs with this as a basis. This is not something I've done by myself. I'm very grateful to all the collaborators I've had on this work. And they've come from a variety of different areas as well. So to summarize, I hope I've given you a picture of what some of the education grand challenges are and some things that I've worked on to look at them. And with that, I'm happy to take any questions. Thank you.